the son of a businessman, so he's around a lot of math sequences as a kid. And so he found the Fibonacci sequence when he was trying to solve the rabbit problem that we had for homework the other night, where you have a colony of rabbits, and you begin with one pair of rabbits, and then they breed, and how many rabbits you have after X amount of months, and it's the pairs of rabbits. So the sequence itself is a series of numbers where you can find a number by adding the previous two numbers, and the equation for it is, I'm going to write it out because we don't want to do subscripts, is n minus 1. So if you have, for example, like 5, looking for 5, or what the, so the fifth number in the sequence, you take the fourth number and the third number, add them together to the fifth number.
Okay. So the golden ratio is the ratio you get by dividing a number in Fibonacci sequence by its predecessor. So, and when you take golden ratios, they all start approaching phi, which is a Greek letter, and it symbolizes the number 1.618039. And as you progress along the Fibonacci sequence, they get infinitely closer to phi. And here's another way of using the golden ratio to find the Fibonacci sequence. Okay, so the golden rectangle. Here's my golden rectangle. One of the ways that it shows up in nature and geometry and all that is the golden rectangle. And the golden rectangle is a rectangle that is the most aesthetically pleasing to the human eye. And you get it and it's a rectangle whose longest side plus its shorter side divided by its longest side equals its longest side divided by its shorter side, and those all equal to phi. And that's obviously just Fibonacci numbers, because see a plus b over a, that has to be if you just look at it in terms of Fibonacci sequence, 1 plus 1 over 1, that's 2, and then it goes on, and that's the phi, and that's how you get a phi by going along the Fibonacci sequence with the next numbers.
Okay. So Fibonacci in plants. So this plant here, if the sun, so if the sun is, say, up here, these leaves down here are not going to get enough sun. So plants have solved the problem of where to place their leaves by using the Fibonacci sequence. And this video might go a little bit fast, but I'll explain it if you don't understand.
Those are the same numbers unless I get these squares. Now stop being a number theorist and start being a plant again. You put your first leaf somewhere and the second leaf at an angle which is 1/5 of a circle, which, depending on whether you're going one way or the other, could be about 222.5 degrees or about 137.5. Great. Your second leaf is pretty far from the first, gets lots of space and sun, and now let's add the next one 1/5 of a circle away, and again, and again. You can see how new leaves tend to pop up in the spaces left between old leaves, but it never quite fills things evenly, so there's always room for one more leaf without having to do a whole new layer. It's very practical, and as a plant, you probably like this.
So plants in their leaves use the Fibonacci sequence to know where to place them. But even if you look at the inside of plants, for seed pods or anything, you're going to get Fibonacci number of spirals. So this has 34 spirals in one direction and 21 spirals in the other direction, which are both Fibonacci numbers. Even pine cones have 8 spirals and 13 spirals. So everything looks good, right? But not
It would also
quite.
be a good way to give lots of room to seed pods and petals and stuff. Get spirals of 5 and 8 on this flower, 5 and 8 on this artichoke, 5 and 8 on this pine cone. Even this cauliflower has 1, 2, 3, 4, 5, 6, 7. Anyway, we always get 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4. It's easy to dismiss these as mutant anomalies, but just because they're different and unusual doesn't mean we should ignore them. 4, 7, 11? What could these numbers mean? Maybe things aren't as simple as I thought.
So these numbers are Lucas numbers. So Lucas numbers, like Fibonacci numbers, start where it's 1, then 3, 1 plus 3 equals 4, 4 plus 3 equals 7, etc. Also with Lucas numbers, when you take a Lucas number and divide it by the Lucas number right before in the sequence, you approach Phi. So Lucas numbers and Fibonacci numbers are very similar. So why would a Lucas number appear? Well, a Lucas number might appear when either 2 leaves start growing at the exact same time, or when there's something else that goes slightly wrong in the plant. Okay, so the Lucas angle is 99.5 degrees in plants, and the Fibonacci is 222.5 degrees in plants, and there are different ways of calculating them, but I'm going to skip ahead for a second. And other places in nature, there's the Lucas spiral, the Fibonacci spiral, sorry. We start with a 1 by 1 box, and then 2 by 2 box, 3 by 3, 5 by 5, 8 by 8, etc. We get the Fibonacci spiral, which is used in shells, even in eggs, and hurricanes. And then if you look hard enough, you can find the Fibonacci spiral anywhere, and someone even found it in Africa. So the whole continent is a giant Fibonacci spiral.
Okay.
So yeah,
You guys stop.
that's it.
Good. Very good. Very good. Okay, we have 3 minutes for questions.
Do you have any questions? It's been amazing.
No.
Are there any like the difference between the Lucas numbers and the Fibonacci sequence? Obviously they're similar, but what is there any like structural, like what is there a difference in how different things with one of them versus the other would behave or something, or is it just
They're pretty similar. They just have like a slightly different number of spirals, and the plant will behave just as well. It just because it settles into the same pattern of putting the petals or the pine cone things into where there's room to grow. So it behaves very similarly.
So the Fibonacci sequence, the nth Fibonacci number is found by adding the nth minus 1 Fibonacci number plus the nth minus 2. How do you find a Lucas number?
It's the same thing.
Yeah, but how does it start? Because Fibonacci you start 1 and 1.
Lucas starts with 1 and 3, or some people even say it starts with 2 and then 1, but that's a little bit of a discrepancy because it goes from a higher number to a lower number. But basically it starts 1, 3, then it keeps going with 4 and etc. 7. Yeah.
Any more questions? Matt?
Your calculation for phi, is phi an exact value? Does it have a definite value?
Well, like, phi is an irrational term, like pi, so it just keeps going. I'm pretty sure it's an irrational. Oh, Because whenever you look it up, it has like dot afterwards. So I'm pretty sure it's an irrational term.
But
Like pi.
there is a way to calculate it.
Yeah, but it's irrational because it keeps going on, and you can never have a definite answer to it. You can only have like approximations. Like pi has an infinite amount of digits. Phi, I'm pretty sure, also has an infinite amount of digits. Why you can never actually reach phi with Fibonacci sequence.
That is correct. That is correct. That's what Wait. Any other questions? Okay, very good. Very good.